Hello, my name is Alexandru Calotoiu, and I will talk today about lightweight requirements engineering for exascale co-design. The title is quite long, but the topic is actually quite simple, but I believe quite important. Uh, to discuss the co-design in HPC systems and applications, we need to consider the applications which commonly run on these systems and the fact that the mix and type of applications varies across different supercomputing centers. So deciding what application and what specifications a next system should have, how money should be spent, is a challenging question. Should we get a system with a lot of CPU power, so fast CPUs, strong CPUs? Should we get efficient and fast interconnect? Should we get fast or more memory? In my opinion, one of the best investments one can make is in better algorithms, improve the applications themselves. But of course, we always need new systems every couple of years. And unfortunately, when deciding such new systems, a lot of the times the decision is based on back of the envelope, very simple approximations, something which in German would be called a Bierdeckelrechnung, so something on the back of a napkin, effectively. On top of this, when making these decisions, we are commonly looking at the performance of the current applications we have on our systems. And current performance might be deceptive. An application whose communication and computational component have requirements which are balanced at a given scale might not exhibit the same behavior when scaled up. Suddenly, the requirements might change as we scale the application to a larger system, and suddenly we have a huge imbalance. One way around this is to create hardware-specific performance models, which provide us with a means to reason about how an application might perform on a given system. However, this means that we create many models. So we need n models for the n systems we have. And then, of course, we multiply this by the number of applications we have to consider. And suddenly the amount of work required to do this is no longer feasible. Of course, parameterization can be practical if the systems only differ quantitatively. But we want to go one step further than that. And we want to define a set of hardware-independent, application-centric requirement models. We will show how one such model can be then instantiated for multiple hardware systems and allow us to compare them with significantly less effort, which would reduce at least one of these two dimensions when considering the workload of a system. And there is one central assumption and comparison we use to create our approach, namely that just like the human metabolism, there exists a data metabolism at the hardware-software interface, and by analyzing that, we can derive valuable insight. Now, on to the details. What does it mean to have hardware-independent requirement metrics? Well, imagining a parallel system from this point of view, we have storage, so just the capacity. Then we have, of course, a memory connection leading to the central processing unit, so the processing unit, and then a network interface leading to a network connecting it to the other processing units. We can therefore look at where data is transferred from one to the other, so from memory to CPU, from CPU to the network, and start identifying these metrics. The first metric, and this one is not like the others because this is a hard limit for most applications, is the number of bytes used in memory. So how much memory we need to run an application. This is the one non-negotiable metric because the other metrics, as I will explain, if we go over budget, so to speak, our application will run slower. If we don't have enough memory to load an application, the application won't run at all. The next metrics are the number of floating point operations an application needs to perform to finish its work, the number of loads and stores it performs, and of course, the number of bytes it sends and receives over the network. An important aspect of this is that the metrics I've discussed so far are, barring some local optimizations, not depending on the hardware at all. These are just something which the application itself needs to perform. So no matter on what system I want to run my application on, these values won't change. How the runtime of the application, what the runtime of the application will be on the system, that might change, however. We agreed, however, that the number of loads and stores alone are not a sufficient metric to describe the traffic of data between CPU and memory. So we also add the stack distance as a measure of locality. How do we gather these metrics? Well, we use existing software for that. So for computation, network communication, and memory access, we leverage SCORP, an automatic instrumentation framework, and the PAPI suite. For the memory footprint, we just use GAD-R usage, and for memory locality, we use ThreadSpotter. All of these are relatively straightforward with the exception of ThreadSpotter, which I will describe in more detail. There is one implicit assumption in our approach here, namely that we are dealing with MPI-based versions of codes. So high-performance codes are commonly run using MPI or MPI and some other paradigms such as OpenMP. Now, back to ThreadSpotter. This is something we use to model locality. It is a metric used to describe locality independent of the hardware itself, which is our requirement. So there are two aspects to this metric. So one is called reuse distance, the other is called stack distance. I will introduce both, but the one we have to focus is stack distance. The reuse distance first counts how many accesses are between two consecutive accesses to a variable. So for example, we have an access to B, then we access C, and then we access B again. So the reuse distance would be 1. Stack distance is a refinement of this because it only stacks unique accesses. Well, in this case, it would be the same, but if we look at A, the reuse distance is 3 because we have an access to B, then another to C, and then another to B, totaling 3. But if we count unique accesses, the stack distance is only 2. Now, with this, we have our set of hardware independent requirement metrics, which we can gather from empirical experiments with these tools, and we wish to then model them. To do this, we use XtraP, which is a tool for automatic empirical performance modeling. What it does is instrument an application, run a number of small-scale measurements, and generate human-readable multi-parameter performance models out of them. This is a convenience, not a critical component to the process, but it does allow us to analyze these results in a, we believe, interesting fashion. Another limitation of empirical modeling is usual that the results are, of course, affected by noise. However, the requirement metrics have the advantage with the exception of load, stores, and locality, the metrics we gather are virtually free of noise, leading to a very good quality of models. So the vast majority of models that we have no error at all. So we can generate perfect models for them. Now, what we did to evaluate our approach is we have introduced a workflow of HPC applications, so a set of them, a workload. And these are Kripke, a neutron transport code, MILC, a quantum chromodynamics code, LULESH, It's Lagrangian hydrodynamic solver. Icofoam is a CFD solver from the OpenFOAM framework, and Riemann brain plasticity solver. And these are, we have selected them to be all HPC applications, but to be different HPC applications, hopefully with also different requirements. Now, for each of them, we gather these experiments, create metrics, create models, and then we show these models. Now, to rank these the growth of these requirements, we vary the number of processes and the problem size per process, and we model each of these requirement metrics. We make the simplifying assumption that on a per process basis, metrics should grow proportional to the problem size per process, but should remain constant with respect to process count. This is not true for all applications, but at least gives us a basis for our comparison and our analysis. Looking at the results we have for Lulesh, for example, we see that this assumption mostly holds for the problem size aspect of it. We have not perfectly linear behavior. There's a small logarithmic term there, but this is not as true for number of processes. We seem to have an increase in communication and computation with a small polynomial component and a small logarithmic component. This is not this will not limit the scalability of Lulesh, but it will slow it down somewhat. Now, we repeat this for all applications, but we don't go into detail now of what the models are for each of them. For that, we can look at the paper itself. But the idea is that for the first 4 applications, we see either negligible growth or very slow growth for these requirements, meaning that these applications are likely to scale very well. Icofoam, however, has some problems, namely the communication grows very, very quickly as the program scales up, and so do its memory requirements, which means that it will probably not be able to scale to Exascale in its current version. Now, what do we do with these models? Well, we increase the problem size per process until we exhaust the memory capacity. Then we compute all other requirements using the models we have previously generated. And now we can discuss 2 different case studies, one considering a relative upgrade and one considering potential Exascale systems. Now, let us assume that we have an existing system and we are debating how to upgrade it. And the 3 scenarios we are focusing on is one where we double the number of racks altogether, or we increase the number of sockets, or we provide more memory. Now we want to see how this upgrade would affect each of these applications. To do this, we first apply the change to memory per process and number of processes to our models. First, we compute the memory requirement, which stays the same as for Lulesh. This did not change as a function of number of processes, which means that the overall problem size can be doubled. Now, using these new values, we can also compute the new formula for floating point operations, and very importantly, the ratio to the old one, which expresses how the pressure on that particular subsystem, for example, computation, will change. And we see that it grows with a small component. So 2 to the 0.25 times 1 plus 1 over log p. We can simplify this and say it grows somewhat like 1.4 as a factor. The same goes for the byte sent and received, so for the network communication. And for the loads and stores, it effectively stays constant. Now, we repeat this process for all the application and all 3 upgrades. And we get this table with how the ratios change for each application. I've simplified the numbers here to only contain to the nearest digit. And we have also added the baseline under the assumption that there is a linear relation between problem size and requirements per process. And we can see that this, for example, for Lulash, and overall it's quite nice, with the exception of memory access when we double the socket, and the problem size per process and the overall problem size, which has a small impact if we double just the memory. Now, this means that we can also see which applications benefit most from which upgrade. And we also see that Kripke and Milk are the ones which can adapt best to all possible scenarios, with the exception that Milk has a small problem with memory accesses, especially when doubling the racks. And Kripke would be the one which can adapt to all situations with the least amount of optimization. But this is not the only thing we can do with this type of requirements engineering. We can also think about absolute values, not just relative examples. So now we consider 3 exascale strawman systems. Very simplified. One is a massively parallel system with many weak processors. One is a vector system with few powerful processors, and then a hybrid, which is somewhere in the middle. We assume we have a total memory of 10 petabytes, and of course that the overall computational power of the system is 1 exaflop. Now we can then try and see how the different applications would adapt and could run on each of these systems. We don't consider icoform for this analysis because the memory requirements won't allow it to fully utilize any of these 3 systems. And we first consider what the maximum overall problem size is on each of these systems. And then we want to consider how fast a benchmark problem would run. And by benchmark problem here, we define the biggest overall problem that can be solved on all systems such that we can compare. So we still use all processors with the adapted problem size per process. And here we see that because of how their requirements are shaped up, Kripke and Milk have the same behavior on all the 3 systems, meaning they can adapt equally well to all of them. However, Lulash provides us with a choice. So it can run a larger overall problem size on the massively parallel system, but would run more efficiently on a vector system. For read-on, for example, here the vector system is a clear winner. Now, of course, choosing which system would be best for a particular workload is a policy decision depending on the goals of a particular supercomputing center. But this type of analysis still can help both designing of systems and to prepare applications for upcoming supercomputing systems and how their requirements must change to adapt to what will be available. So in summary, we have generated a way of creating application-centric requirements models. We do not need to integrate the hardware knowledge into them, and we are trying to generate them using existing profiling tools, including even memory locality. And we can use this to either extrapolate requirements to new systems and point bottlenecks out both on the application side of things and point out which parts of a future high-performance system will likely be the bottlenecks for a series of applications. So in effect, we are trying to automate the back of the envelope decision for co-design in large workloads. Thank you very much, and I will now take your questions.